let's just dive right into it. I am going to talk to you guys today about explaining a black box model's decisions. And as Ayelan said, I work on machine learning here at Stripe, and so this is going to be a more ML-focused talk. And you also got a lovely description of what Stripe does, but since I'm up first, I have the obligatory, what is Stripe, and why are we trying to solve these problems? Stripe processes payments along with a lot of other things for online businesses. So we use machine learning for a lot of different things, but I like to think sometimes that we use machine learning to do magic. This is sort of the what my friends think I do version of machine learning. You do magic, you give some data to a computer, or you sit the computers down in a room and teach them to do cool things. Sometimes my friends get less happy about machine learning and they consider it a sausage factory. They're input goes in, something comes out, it's tasty. I don't really care what you're doing under the hood. Just give me the right answer for what your model is doing. I'm going to tell you a little bit more about what we do and why we don't think about machine learning as a sausage factory, but instead try to understand what's going on in the internals of our models. So the way that we apply machine learning at Stripe, or I guess one way that we apply machine learning at Stripe, is to prevent what we call transaction fraud. So transaction fraud happens when the business that is using Stripe to take payments is a good business. I'm happy to talk more about what a fraudulent business might look like, because that's very interesting. But in this application, the business using Stripe is legitimate, but the charges being made on the business's account are not authorized by the cardholder. So if someone steals your credit card and tries to go take a Lyft ride, that's the kind of thing that I want to try to stop with my models. So Stripe automatically will decline charges that we think are risky or sort of not authorized by the person that owns the card. We use what we call a random forest to do that, and I will get into the details of random forests, but the idea is it's basically a large set of decision trees. Now, we use some large set of decision trees to decide whether we're going to process your payment. And it turns out that people care, you care, and our businesses care what decision that forest makes and why. And so this is not true only at Stripe, but this is true as sort of any product-driven company. And you might even be able to see this on sort of your social media accounts. You can click on some ad that you see, and there's usually a button that says why am I seeing this ad? People care about what decision was made for you and why you made it. So back to the random forests, there's actually kind of a fun challenge in trying to tell people why a random forest made a decision. So we will try to dig into that right now for a little bit and see what's what. So I know there's probably a wide variety of experience in the audience, but as sort of a schematic of what a random forest is a set of decision trees which might look like this. So for every charge, we would basically start at the top of the first tree and ask a question, and then we would follow the decision tree down to some terminal leaf. So for example, if you have a card that was issued from a bank in the United States and it has had more than 12 charges on it in the last 30 minutes, we would maybe say the probability that that charge is fraud is 81% based on the sort of data we've seen before. This is just an example. This is not real. So yeah. So this is just an example of what a tree looks like. And a forest is a big giant set of trees. They're not all the same. Some of them have different questions in them and use different sets of data and use different sort of properties of the charge to make their decision. But there's basically a big forest of trees, and it sort of votes on what the forest as a whole thinks about each charge. So the final decision, as I said, was made by sending the charge through all the trees and averaging the predictions. And so this tells you what decision should I make for this item. And so the problem actually comes when you try to explain why. So some business will write in and be my friend tried to buy my product and their card got declined. Why did you do this to me? How did this happen? And we launch into some long paragraph trying to explain its path through this gigantic forest, and it is kind of terrible. So we are sad, and that is unfortunate. And so I've described random forests, which are sort of like relatively tractable. If you're using neural nets to make decisions, I am even sadder about trying to explain like what the neural net was doing and like why it thought that the sort of, why I thought the pug was a blueberry muffin. It's interesting. So it is kind of hard to like actually dig into like what a black box model is like doing to understand why. There is a solution, and the solution is like not to panic. So that was like actually the main breakthrough that we had when we were working on this. So we actually started working on this a couple years ago, and the first thing we did was the easiest thing that we could think of. And so version 1 of trying to explain why Stripe's fraud models were declining charges went something like this. The first thing we would do was sort of estimate the model's probability of a probability that the charge was fraud using all of the charge's features. And then we would sort of like iterate over each feature that we were using to predict fraud, and we would make that feature missing one at a time. So we would like, get like a fake probability of fraud, assuming we didn't know the brand of the card velocity, etc. And then we would basically take the deltas of those bottom level predictions between that bottom prediction and the like actual fraud prediction. And then we would circle the feature that like gave us the biggest change. So if we sort of had some charge that was fraud, and when we removed the card velocity, its prediction changed a lot, we would be like, oh, the card velocity is the thing that is driving this prediction. And we would like have some nice English, and we would say like this card number has been used an unusually large number of times in the past hour. That is what our model is doing, and that's why we think it's fraud. This was like kind of mostly okay. If you think about this, this is not, this is not obscure science. This was sort of something that we thought of that like might work, and it actually helped us understand our models quite a lot. So we like found some bugs. We found out that like, for example, like some of our businesses were doing card present transactions, and they were using all the same IP address, and so we were like getting confused by that, and we like weren't able to see that until we started surfacing like IP address as our predictors. So this mostly worked, but we needed something a little bit faster and a little more formal if we were going to ship this to production, which we actually did in October of 2016. So before that, we actually implemented V2 of decline explanations. And this is based on a paper that's called a model explanation system, and it's specific to random forest. I have these slides available afterwards if you guys want the paper references and things like that. So the procedure in the paper goes something like this. You basically build a model on top of your model. So you have your like random forest that you have, and you're like, great, I'm going to build like some meta model on top of this forest prediction. And so what this like new model will do is create a list of explanations by generating combinations of a few predicates from the random forest. And the predicate is what we call sort of any like yes or no decision from the tree. So an example, like there's 2 predicates in this explanation, and this whole thing is considered an explanation. So the predicate is something like the card was used more than 3 times in less than 30 minutes. So the like model will traverse your whole like fitted tree and like extract a bunch of these explanations that exist. So once the explanations are extracted from the tree, they are ordered by their precision. So basically, like of these explanations, like of these sort of explanations that can be true or false of any item, like what percentage of charges satisfying the predicate does the model say are fraud? So if that's really high, that means it's like a pretty good explanation for like why something would be fraud. And then the third step is basically make sure you generate enough explanations so that the set as a whole has good recall, so that you like cover all of your predicted fraudulent charges with like some explanation that you can pull out from the tree. And so this works really nicely because then sort of in production, as you're processing charges, you can just like go through this ordered list of conditions. And if the charge is predicted fraudulent, like you can just like stop at the first condition it satisfies and like pop that out as the charge's explanation. So it turns out this is like what we do. So this is, if you've seen the Stripe dashboard, if you click on like the radar panel, you'll get little sentences that tell you why Stripe declines charges charges as fraud, and that's how we do it. So we like train models automatically to have these sort of like explanation models on top of them, and we show these to our businesses. So this is kind of an interesting problem. A question that I often get when I give this talk is like, cool, you're like doing fraud modeling, but you're basically telling people what things you're using to stop fraud. Like, what if you tell a fraudster how you're finding fraud? So this is like, we're sort of like creating an adversarial situation for ourselves in saying what we look at. So I'm happy to talk more about the challenges there, but this is sort of the product challenge here is like, how do we write something that is useful to the business owner, but not so specific that someone could like reverse engineer how to get around the algorithm. So I'm happy to like chat more about this at length at any time, but I'll be around afterward if we want to like talk more about like the challenges in actually doing this. So I think like the main takeaway from this talk is sort of like explaining why models do things is actually like kind of important, and I think often sort of in the machine learning research world, it's not like a huge focus, but it is an interesting product question. So it's possible, and we shouldn't let that like stop us from trying to figure out what's going on. So that's it. My colleagues Tom and Eric actually did the implementation of these explanations. I just talk about them. So they did lots of work, and you should look them up because they're very smart. But yes, I have. I'd be happy to like take questions. I think we have like 3 minutes until the next speaker. Otherwise, I'd be happy to talk to you guys after. So thank you.
So I was wondering about the random forest methodology. What part of that is random? Is it the decision trees that are selected, the order that they're processed, or something else?
Yes. The part of the random forest that is random is basically there's a subset of the data that is used to fit each tree, and that is randomly selected. And then actually in a single tree, at each split of the tree, there's only a randomly selected subset of the possible predictors that are used at the splits. So you basically get like, it's hard to overfit them because you're not using all of your data in any one tree, and you basically like, try to get a better prediction for a charge that is not in your training set by sort of like leaving out some of the data there. I think I got the details right on that. But yeah, the randomness is sort of in like how you sample your data points and how you sample your features at various places in the forest.
Okay. I'm curious how you address the challenges of not giving the potential fraudulent business too much information.
Yes. That was a free question. The main way that we do it is there are some things that we actually don't expose. So the first, if you're on some sort of for example, if this card has been used on like a known fraudulent account in the past, we don't say like, we saw this used on a fraudulent business in the past. We'll sort of like say something a little bit more generic. But the other thing is sort of like trying to say like what we thought, but not like the specific value or the specific other interactions that we saw. So we'll say something like, this card has been used an unusually large number of times in the past whatever, but we won't say like how many times, and we won't like promise any sort of specific cutoff like that. So it's like sort of like, well, we're kind of okay at telling fraudsters that like, yeah, we look at like card activity in the last day, like most people kind of know that. So we kind of like cut that loss. There were a couple things that we sort of were like, how do we explain this in like usable ways? So we had to like think of a sort of layperson definition of like anonymous IP address. Like, so we sort of said like, we think this IP address is being sort of hidden in some way. So we chose to like expose that, which maybe means that people will switch ways to obscure themselves. And so we have to like work to develop methodologies to detect other sort of, masking technology. But we sort of like try to stay on top of that. But yeah, so staying general and like cutting our losses and like actually like thinking of what the effects might be if we share some information and like taking on that work as well. So one more question.
Hi.
Hello.
I'm curious how you, if there's any way that you can incorporate user feedback into your meta model. So how do you like iterate on what you are showing to not organizers, like businesses, like from a usability standpoint?
Yes. Is there?
Like, how do you know if what you're showing to your businesses is useful to them?
Oh, yes. This is actually a hard part about training these models, because in the explanation model, there's like not a right answer often. Like, the right answer is like, well, it went through all of these trees, and this is like the majority vote of this thing. We've had some people do manual review, and we've also, like, we pay attention to like what people file tickets about. So I think we just introduced there's a tiny little widget that pops up in your like Stripe dashboard that says like, do you have any feedback? And you can also like write into our support address. So we've like collected the tickets, and we get a lot of ones that are sort of like, the people feel nervous when they see that the main explanation is like the card country does not match the merchant country, because they're like, I have people from all over the world ordering from my site. And so there's a lot of communicating like, this is only one reason. There were many factors that go into this prediction. And then like the sort of reasons that we get the most feedback about are the ones that we try to give less weight to in the future, or ones that we sort of try to be like, well, maybe we should like actually look at the second most important, predicate. So like each example has 2 predicates. If we like drop one of them from the possibilities, we can like use the other one. So there are like ways that we sort of try to make these more useful. But of course it's like hard because it's difficult to get automatically labeled examples for this kind of thing. So great. Okay, I think that is all the time, but thank you very much.
Hey everybody, my name is Faye. I'm a product engineer on Radar. So I actually work on a team that uses the ML models that Alyssa was talking about earlier. So part of being a product engineer is that we pretty much build whatever is necessary to get our product out the door. For Radar, that means we want to basically create a product that will help our merchants by figuring out like what a charge, whether or not a charge is fraudulent, and then either blocking that or helping them prevent like getting disputes. So today I'm going to be talking about building a simple DSL with Parselet. So let's define some terms. What is a DSL? DSL stands for domain-specific language. So that would be a computer language with limited expressiveness focused on a particular kind of problem, like a business application. So this would be different from a GPL, which a lot of you have probably worked with. GPL is a general general purpose language, for example, C++ or Ruby. Basically, it's a very powerful language that allows you to write your own program with whatever structure and whatever algorithms that you want to. So a DSL would be a very, very limited, would have a very limited scope and functionality, and it would do like maybe a couple of things, whatever you define it to do. So there's 2 different types of DSLs. There's internal DSLs and external DSLs. So an internal DSL is sort of like a mini language that's defined in the language, or well, it's written in the language that it's also parsing, or it's written in the language that, how do I explain this? Like, it's written in its own language. So for example, Rails or Rake, they're often called fluent interfaces. So it's kind of like an object-oriented way of defining APIs. So like a class structure with some different methods that you would define in that. In the same language. So this is different from an external DSL, which is often used to parse a language that you've constructed. So it's like a totally different language. For example, if you've used regex or SQL, so those would be examples of external DSLs. So stepping a bit back, why do we care about DSLs? Why do we need one? For Radar specifically, we want to give merchants the ability to write their own rules. So Alyssa talked about the machine learning models that go, so a charge comes in, the machine learning models evaluate, okay, how likely is this charge to be fraudulent? And then based on that, it's like high risk or elevated risk or low risk. But then what do we do with that? we want to give our merchants the ability to decide what to do with the decision from the machine learning models. So we have a rules engine that we've built, and that allows our merchants to basically write their own rules saying, we want to block the charge if the model says that it's risky. Or we can take some risks, so we only want to put them in review. Or we don't even want to block them at all, we just want to allow the charge. So this is a sort of a look at the types of rules that we allow our merchants to write. So when should a payment be allowed? So like allow if the payment has gone through 3D Secure, which is like a verification process, or block if the risk level, which is the level that comes out of the machine learning model, is highest, or place in the review if the risk level is elevated. So in order to allow our merchants to write their own rules, we have built out a parser on the front end. So basically, we wanted to define our own DSL for our business application. So a rule would look something like block if the card funding is, in quotes because of the string, prepaid and amount in USD is greater than 1,000. A lot of merchants will have some kind of rule like this because it likely means that someone stole that prepaid card and they're trying to buy something with it, and they don't want to, they would want to block that charge. So looking at this rule example that we've put on here, block if card funding is prepaid and amount in USD is greater than 1,000, we kind of see like a little pattern of what the language that we want to define will look like. So we see action, that's the block. We have a couple of options. We have block, or maybe we want to put in review, or we want to approve the charge. And then we have if, and then a condition. So the condition here will evaluate to a Boolean. So it'll be true or false. It'll be card funding equals prepaid and amount in USD is greater than 1,000. And that'll either be true or false, and that determines whether or not we take the action. So if we look at that even further, let's take just the amount in USD is greater than 1,000 part. We notice that it's attribute, operator, and then value. So the attribute, which is the amount in USD, we have over 40 plus attributes that we give merchants the ability to write rules on, such as card brand or IP country or declines per IP address daily. You can imagine how that could be super useful for a merchant. If some IP address has been processing like 1 million charges in one day, there's probably something sketchy going on there because like one person couldn't be like processing all those charges. And then we have an operator, so that's like our greater than sign, and then 1,000, so in this case it's numerical, but you could also have a string like the prepaid one. So in order to construct our DSL, we have chosen to use a very small library called Parselet. It's really, really great. It's super easy to use, and it has a lot of advantages that I'll talk about very soon. So Parselet allows you to write a DSL or define a DSL in the parsing expression grammar fashion. So that's when you have a set of rules to use to recognize your string in your DSL. So here's like a very, very simple example of a DSL. 1 plus 2 plus 3, which is like addition. We would break that down into a tree, which is a set of rules. So at the top level, we have operators, like plus, the plus symbol. And then we also have the data nodes, like the 1, the 2, the 3. You can also define other things like cosine of pi, or really whatever language you want. The important thing to note here is that for parsing expression grammars, the tree that's evaluated, so like the structure that comes out, is not, it cannot be ambiguous. So there's only one tree that comes out of any string that you're parsing. So this is very different from a context-free grammar, which is ambiguous, and you could have one string and parse it in several different ways. So actually, the example of 1 plus 2 plus 3 might not be that great because it could also be used as a context-free grammar, since in addition, it's cumulative. So 1 plus 2 plus 3 is the same thing as 2 plus 1. 1 plus 2 plus 3 is the same thing as 2 plus 1 plus 3. But if you were going to use Parselet to define addition, you would only be able to write your tree one way. So that would be like, do the 2 plus 3 first, then the 1 plus. So to use Parselet, you need to define a parser, a transformer, and then an evaluator. And I will go through what these are. So stepping back into the radar example, block if card funding equals prepaid and amount in USD is greater than 1,000, we define the operators, so that would be our and, the equals, and the greater than. And then we also define the data, which is really important because that's what you're doing operations on. So our data here is like either string or numerical or an attribute. So our attributes are card funding, amount in USD, and then the string is prepaid, numerical is 1,000. So here's like a little snippet of like what your parser might look like. I hope you can read that. So you want to define what a single character is. So a single character is like the colon or the A or the 1. If you see, for example, you match 0 through 9, you repeat at least once, then you know you have an integer. So then you construct like a token out of that. Then you have like the operator, for example. Here in this case, it's a single character, which is the greater than sign. But you can imagine that if I wanted to, let's say, spell out greater than, I could just say match with the GREATER, et cetera, et cetera. Then we want to define the grammar parts. So Parselet has both look ahead and look backward for the grammar. So here we do, if you see an attribute as the left side, and where attribute is defined as colon, match some string colon. And then you see an operator, which here is a greater than. And then you see an integer, which is match one or more numbers. Then we define that as a comparison. So Parselet would go through this and would be like, oh, okay, amount in USD, this is an attribute. Greater than, that's an operator. 1,000, that's an integer. And you would define a root, and that's kind of like the root of your tree. And this would be a comparison object. So then you go on to the transformation part. So basically, like now you have Parselet recognizing that amount in USD is an attribute, greater than is an operator, 1,000 is an integer. But you need to give Parselet some way of using that. You need to define like what are we actually going to do with the data and the operators, because I mean we all know what greater than means, but the computer doesn't in this case. So we transform this into an object that's going to have an evaluate method on it. So the transformer and the evaluator are highly related. So here in the transformer, we basically just say, if we match the left side and the right side, and the operator is a greater than sign, then we create an object called a comparison node. So this will be our comparison node. We make a new one. We say we give it the left side as an attribute, the right side as an integer, and we do an evaluate. And in this case, it's actually very simple because Ruby actually recognizes the greater than sign. So you can just do the left side, greater than the right side, and that will evaluate to either true or false. So in short, we take this amount in USD greater than 1,000, and we're able to come up with true or false. But you're probably wondering, like, okay, well, where do we get the amount in USD? So this is an attribute that's computed on every single charge. A charge, of course, has an amount of money that's moving with it. So we go back to the charge that the customer has made on a merchant's website, and we pull out that number and we actually stick it into the attribute here. So we find wherever we match something called an attribute, we look back to the charge in order to fill that in. So in this case, let's say it was 600. So we would fill that in with 600. And now we have something we can fully evaluate in Ruby, which is 600 greater than 1,000, integer compared to an integer. And in this case, we would get false. So it's pretty simple to write a DSL. Obviously, I've showed you just a snippet of the code, but you can imagine like all of the possibilities that you could come up with in order to define your own language for whatever business application that you have. Here at Stripe in particular, we wanted to give merchants full flexibility over rules, and so this is something that we've chosen to do. Thank you. I have 2 minutes if anyone wants to ask questions.
Hello, thank you for the presentation. I have like high-level question. When you decided to build this DSL, you built it to serve clients who are not developers, right?
For the most part, yeah.
So what's the advantage to allow people who are not engineers write and then build a parser to read all this grammar versus having like an interface for building rules?
Yeah, good question. So we give our clients this sort of almost free-form looking box that they can put text in, and that's really to give them some like full capability of writing like really whatever kind of rule they want. I wrote a pretty simple one. Most merchants write pretty simple ones, but you could imagine that they would write something like, put it in review if the amount in USD is greater than 100, and oh well, my business doesn't operate in Canada, so and I'll add another clause saying like, and the IP address is in Canada, and then you're like, oh well, also I really don't even have anything that costs more than $5, so maybe I should like add that in the amount too. And so they can like keep stringing all of this into like nested ands, like or and then a huge and clause. And I think that it would be very difficult to provide that kind of rule writing capability in the form of like, let's say, a more visual interface like drag or like drop downs. But I mean, you could also have like a more visual interface. But in the end, like whatever your interface gives you, you as in the machine, you still need a way to evaluate it. And that's like, you can still use the evaluation and transformation part of Parselet or whatever DSL writer.
Can you give like an estimate on adoption of using these language writing rules versus interface? Because interface is usually more intuitive, and especially if you do not expect customers to build very complex rules. So, like, not how many users actually use it, but maybe you can give some insight on adoption of this service. Thank you.
We've always given them the ability to write out like string formed rules. Actually, we didn't have like a drop downs or buttons, and we've generally found that merchants are like understand it pretty well and will use it to write their own rules. I think it really depends on like the people that your product is targeting. For us, it's like business owners. Actually, a lot of them are software developers because they integrate with Stripe as well. So I think they've like generally found it to be pretty good.
What process did you go through to choose which tool to use? Like you ended up using Parselet, and like what did you consider and how did you decide?
I actually wasn't around when we chose to use Parselet, but there are a good number of, so our primary stack at Stripe is Ruby. So if we were going to build it again, we'd probably choose another Ruby parser builder. I think the advantages of Parselet is that it's a fairly lightweight and small library. It's pretty perfect for our use because it's parsing expression grammar. Our rules are, really only need to be parsed into one specific tree. And I think one of the biggest advantages that I see from Parselet is like the really, really easy way of writing unit tests. I didn't really show that here, but you can definitely go check out the repo and like try to write some tests. I think the test writing for parsers can be pretty complex just because you can generate a million different types of trees, and like how do you test that? The tree that's parsed is like actually what you want the string to be parsed into. I think that Parselet has done a pretty good job with their unit testing framework, but yeah.
Hi. In general, I'm a little curious about how you evaluate the adoption of merchants that are using your tools, because they're so widespread and in the industry. You also may not know about that much about this, but how do you evaluate whether it is fulfilling their needs and get that feedback?
Whether rule writing in particular is. Oh, okay. So we have a pretty good idea of what a good rule is versus a bad rule. For example, if you wrote a rule that blocked all of your charges, probably a bad rule. Or if you wrote a rule that blocked none of your charges, that's also probably a bad rule. So we have a pretty good idea of what that means. And if it's a good rule, then it's probably blocking transactions that we would have otherwise would have otherwise been disputed, or transactions that also ended up on like some other merchant's block list or something like that, and that's probably a good rule.
So you're doing it based on like the internal data that you already have instead of like actual feedback from them?
Oh, the rules are written by the merchants themselves.
Yes.
We have a couple of default rules, like block if the machine learning model says that the risk level is highest. But other than that, like the merchants can write their own rules. And it is like pretty difficult to explain to a user like what a good rule versus bad rule is. The best thing that we've done is we give them a set of docs that says like, that explains like what every attribute is, and it says to like evaluate your own business and figure out like what's best for your business, because each merchant knows their own business the best, and knows like what fraud. Usually like merchants have a pretty good idea of like what fraud looks like for their business, at least like sort of like, oh, I see a lot of fraud from like I don't know, Canada or something.
I don't know if there is room for another question.
One more.
Real quick. I was just curious because I was wondering, like, for example, of course, we focus a lot on the markets in US and Canada, but the market is, of course, a little bit different, like in Europe, for example. You know, you have different safeguards when people use credit cards in Europe. And I was just wondering if, is there any difference how that works internally at Stripe? Like, do you actually set up different rules for different markets, or is it like, general? And I was just curious about that.
We don't set up any default rules that are specific for particular markets. However, we definitely encourage merchants who are in a very specific market to set up like their own rules. For example, actually this has recently become a default rule, but allow if is 3DS secure, which is like pretty popular in Europe. We encourage like merchants to set up that rule. I'm trying to think. If you know that your business only operates in like 2 countries, and you can set up a rule saying like, I want to review charges that come from other countries. There are countries that are known for having like particularly low levels of fraud. Those merchants who are in those countries might want to relax some of the blocking that we do, versus countries that like countries with merchants that maybe, or merchants in countries that maybe experience a lot of fraud, maybe they want to write like a lot more rules to block. We do encourage our merchants to do that. However, we don't do that from our end. We kind of let them take the reins on that. Yay, thank you.
All right, hi everyone. Welcome and thank you for being here. I'm Pam and I work on the applications intelligence team, where we're starting to do some deep learning techniques inside of the team on the data that we have at Stripe. So if you're like Stripe, you have a lot of interesting unstructured data that you'd like to gain some insights out of, and maybe tease some structure out of that data and try and learn more about your business. In our case, what we want to do is maybe try and figure out how merchants are similar to each other, since we have so many merchants and they're all sort of spread across different countries and different industries and kind of target different kinds of businesses. Understanding that one merchant is similar to another in a semantic manner is pretty interesting to us. Right, so we process lots of payments across different cardholders that actually use Stripe, And for each of these payments, we get a lot of interesting information about it, like how much money was actually being processed for that charge, who the merchant was, and where was the actual payment. And so I'm going to talk a little bit about a popular machine learning technique that's classically kind of used for textual data, and how we actually applied it to our payments data to understand how merchants are similar to each other. So this technique is called word-to-vec, and it was developed by a former coworker of mine while he was at Google. And it's considered a deep learning algorithm, but not really. It's kind of an unsupervised learning technique, which means that we don't need a data set that has labels associated with it. No human being had to go in there and like tag a merchant with an industry or something like that. It's used for effectively processing large text corpuses and is able to learn linguistic regularities like Madrid is to Spain as Tokyo is to Japan. I'm sure like all of you remember that SAT nightmare. And so I'll kind of talk a little bit about how word-to-vec works under the covers so we can kind of understand what's happening there with a text example. And since I like dogs, the example sentence I'm going to use is, "The puppy is cute and fluffy." So what happens with this sentence when we actually present it to this machine learning technique is that it first tries and uses one of the words as a target, and looks at the rest of the words in that sentence as the context. And so in this case, we're going to use puppy as the target and the as cute and fluffy as the context. And you can imagine sort of other words can fit into where the green box is, right? Kitten, bunnies, but probably not armadillo. And so what the model actually ends up doing is building a vocabulary of all of your unique words and assigning sort of indices to each of them. And it doesn't have to be ordered in a specific way. I just kind of set it up so that it's easy to look at. And for each of the words that are in your context, you can effectively think of this as sort of selecting out a specific almost one-hot encoded input vector where for each of the words in the context, we're going to set those to 1. So cute and fluffy will have 1, but puppy actually is set to 0, and everything else is also set to 0. And what this is going to do is project it into a d-dimensional space where we've set up a large matrix that might be 200 wide, and for the vectors corresponding to the indices for cute and fluffy and those vectors will sort of be projected into a specific space, and then we'll try and determine what the probability of the word puppy was. So it might actually give you a little output which says that the probability of puppy was 0.05, which is pretty low. It's not exactly what we want. We want it to be much closer to 1. And so we can actually go ahead and try and take an error with a target vector that has 1 for where puppy would be, and try and move that output vector closer to the target. And then we, backpropagate, as we all do, and kind of learn over time that puppy will have the next time that it sees the sentence or the context, the is cute and fluffy, it'll have a higher probability of predicting puppy or maybe kitten or bunny, but not armadillo. Okay, so that was kind of a grueling exercise, but let's talk about sort of like how this applies to payments. With payments, what we kind of want to do is do something similar to what we're doing with sentences, where we want to know that bunny and puppy and kitten are similar given a certain context, right? And that seems like it would fit the flavor of wanting to detect semantic similarity between merchants. The thing I kind of started trying out was, given the way that the end users of our merchants actually visit our merchants, are we able to get the structure out of there? Is there latent signal available inside of the way that our end users kind of visit our merchants? So for each merchant, I actually represented them as URL domains and constructed sentences for a given end user. So for example, if I visited Indiegogo and Kickstarter and bought stuff on DoorDash, then this would be my URL sentence. And the URL domains are actually just the unique instances of the merchants that I visited. And if someone else visited Indiegogo but not Kickstarter, then they'll have, Indiegogo and DoorDash and Wish.com. And so one of the interesting things that kind of comes out of this particular model is that we have that large matrix that eventually gets shifted over time because we're backpropagating through it. And that effectively yields a feature vector that is n dimensions, where n was whatever we chose to project this into. And this can actually be used to represent what our merchants are in a float vector. And so this can be used as a different signal for other machine learning models or different kinds of applications on Stripe. And you can also apply something like cosine distance to actually figure out if two merchants are similar to each other. And this actually did work. So we were able to detect things like Indiegogo and Kickstarter are similar to each other, and Instacart and Postmates and DoorDash are close to each other. And if we actually apply k-means clustering to this output, this ends up giving us a lot of interesting clusters like education services or wedding services. That was actually one of my favorite ones. There's like several ones where we have like a merchant who just sells beach balls with the word love printed on it. And that's in the same cluster as sort of other things like videographers and bands and bridesmaid gifts and so on and so forth. For the more sort of sparse regions that we actually have inside of the Stripe ecosystem, we actually find that geographic partitioning is one of the ways in which these clusters fall out. So if we have fewer merchants in certain countries, they might actually all cluster together. And this is one of the interesting problems that we're hoping to tackle, and figuring out if we can actually just like force this all into like industry as opposed to having a geographic partitioning show up somewhere in here. Okay, I can take questions for quite a little bit of time here.
Hi. So this is all really interesting. I'm wondering, how do you guys end up using this clustering? Because it seems like the model comes out with all of this interesting data and ways to look at data, but how do you actually use it in a way that solves a business problem for you guys?
Yeah, so I mean, we have several different kinds of applications that might actually find industry-specific partitioning interesting. So perhaps certain industries have higher kinds of fraud, higher rates of fraud than other industries, or maybe we want to actually benchmark merchants against each other to give our account managers some information that they can then take back to the accounts that they actually work with. I think that the actual like applications on top of this are wide and varied, and we're looking into all of those in the next year. So yeah, also looking for people.
I'm curious if you considered other clustering algorithms or other ways you thought about getting at like categories like this.
Well, so a different approach that had been tried prior to this was actually using merchant-specific, what the merchants had provided to Stripe as their description. So we actually did try this technique against text, and also tried to do something like LDA to try and tag different merchants. LDA is unfortunately very slow. And with the actual text data, what ends up coming out of this is that we get the ability to say that, like, given a word, what other words is it similar to, as opposed to given a merchant, what other merchants is it similar to? And so that was actually one of the that was one of it. To be clear, like, the words version of this is actually used for other things, but it's not used for sort of identifying semantic similarity between merchants. Although I think you could potentially use the bag of words that are associated with the merchant's description, sum those vectors up, and like use that as a merchant representation. I just haven't tried that, so.
I'm curious to hear about how you store the n-dimensional vector that you talked about, because you mentioned that other machine learning models can also use it. So is that something that you already store for others to use?
Right now, it's currently in S3, and it's serialized in some simple binary format, so nothing too fancy. And I think Word2Vec just has like a binary format that it dumps out into. There are various flavors of Word2Vec that you can use that will dump it in like different formats. You can also dump it as like raw floats, but that's a lot. I mean, you lose precision sometimes, so don't do that.
For the merchant data, like in terms of what were the SKUs that were purchased in the products, do you guys have access to that, or is that just housed within the merchant? That's question number one. And question number two is, the reason I ask that is, you know, from your example of the love balls that say love, can you then pull in demographic data? Like, for example, a conclusion that women do 80% of the purchasing for their wedding.
Yeah, so the end users themselves, we don't have very much information about them other than sort of whatever comes in with a transaction. Like we don't connect to third-party data sources to try and understand our end users, our merchants' end users. So if we're gonna do something for end users, it's gonna have to be a little bit creative, where whatever feature vectors we do end up producing might actually be like some combination of the first float might be like gender, location, and age or something like that, but we wouldn't have direct access to those as input features. And the first question you asked was, does the merchant provide us with product SKUs? No, they do not. And that makes this tricky.
Thanks. It was really interesting. So my question is, like, what are the high-level patterns that you see between different merchants? So you were saying, like, Indiegogo and Kickstarter obviously had like a lot in common. Like, what would lead you to know that? And then do you see customer clusters that happen that you don't understand the relationships between them?
Yeah, great question. So for the high-level similarity, like it does turn out that a lot of the clusters seem to be like very focused on industry. Like there was one that was entirely WordPress plugins. There was another which was like VPN servers, et cetera, et cetera. So it does, like, a lot of these actually fall into what seem to be very industry-specific partitioning, but there were definitely clusters that I didn't understand, and some of them actually had foreign languages involved in the description, so I couldn't actually parse it myself. And the other was, some of them seemed just like a random collection, so they might just have like a low traffic rate, and I haven't done enough analysis to be able to give you that information, but I expect that that's actually what's happening there. And one more question, I think, in the front. Great question. The question was, do I do dimensionality reduction on this? Not yet. That is actually something that would be really, really interesting to us, to be able to like take our 200-dimensional vectors, turn it into like a two-dimensional vector, and just say, okay, given that, like, what can we do with this information, right? Like including visually representing it in two-dimensional space. So I think the next things that we're going to try is like running tsne on this, maybe doing PCA on it to try and figure out if there's like a distribution over the principal components that might be useful for other models. Thank you.